In the last video, we talked about different possible electric field line configurations based off of different point charge configurations. While we can get pretty neat and beautiful patterns, they're not the most useful to work with in a mathematical sense. So let's consider what the simplest of all possible electric field configurations looks like. This is a uniform electric field. An electric field that could be written in this form, where A, B, and C are constants. To put values to it, we have here 4, 0, and 0. A uniform electric field is a constant electric field. It's constant in space and time, meaning it never changes. Here's another example of a uniform electric field. And another. And another. Notice how the electric field is the same value at all points in space. The natural question now is, how might a charged particle behave in a uniform electric field? Well, let's think back to classical mechanics for a second. We've already seen how a particle with mass behaves in free fall in a uniform gravitational field. The gravitational field has the effect of changing the mass's vertical component of velocity, but not its horizontal component. Why? Well, the gravitational force on this particle is m times g, where m is the particle's mass and g is the gravitational field. In free fall, this is the only force that's acting on the particle. We also know that the vector sum of all the forces on the particle is equal to its mass times its acceleration. If there's no other forces acting on this particle besides gravity, then the gravitational field is the particle's acceleration. This is why sometimes you hear g referred to as the acceleration due to gravity. It's not necessarily true when there are multiple forces involved, but it is true in free fall. This allows us to write useful kinematic equations that define for us the particle's position and velocity at any point in time. As long as we've ensured that the acceleration is constant, we're allowed to use any of these equations here, where the acceleration is based on the particle being in free fall. We can consider a similar kind of analysis with electrically charged particles. Just ignoring gravity for a second, what is the net force on a charged particle in a uniform electric field like this? If we ignore gravity, there's no other force acting on this charged particle except for the electric force, so that's the net force. We also know the net force gives us information about the particle's acceleration via F net equals ma, so the acceleration is q over m times the electric field. In the midst of all this, I encourage you not to be boggled down by all this electricity business. At the end of the day, the electric force is just another plain old force we need to account for, just like all the other forces we've been used to dealing with. So the kinds of kinematic analyses we did in classical mechanics are relevant here too, just in the context of a different force, namely the electric force.